Hello again, everyone. In this video, I'm going to be going over the solutions to the third FRQ practice test in your folder. So the first question here deals with an object that's moving on the x-axis, and you're given its potential energy as a function of position. This is hopefully something you remember us doing back in Unit 3, but it's been a little while, so this might be a good time to review these types of problems. So in this particular problem, we're given sort of three pieces of information about this object. We're given that its mass is 3 kilograms. We're given that its potential energy as a function of x is equal to 4 times x squared. And we're told that when the object passes x equals minus 0.5 meters, its velocity is 2 meters per second. So I could write that like this. Okay, so we have a series of questions here. The first one is to find the total mechanical energy of the object. Before I go into that, one thing I might do is just sketch what this potential energy graph looks like. So if I plot u as a function of x, 4x squared, of course, looks like a parabola centered on the vertical axis, so it should just look like this. And one thing you should always remember is anytime you have a potential energy which is parabolic, that is going to give you simple harmonic motion. So this object is going to oscillate back and forth between two endpoints. You can remember something like a spring has a quadratic potential energy, 1/2 kx squared, and that gives you simple harmonic motion, so that can be one way to remember that. Okay, so for question A, we want to find the total energy of this object. That is going to be its kinetic energy plus its potential energy. So we have to use the fact that we know its velocity at one particular location at x equals minus 0.5. So its kinetic energy at x equals minus 0.5 will be 1/2 times the mass times its velocity squared, and the potential energy will be its potential energy at that location, which is in general 4x squared. So this equation is still general, but if I put in specific values pertaining to when the object is at x equals minus 0.5, I can put that the velocity is equal to 2 and x is equal to minus 0.5. So now if I multiply these out, I'll get 6 joules of kinetic energy and 1 joule of potential energy, so the total energy is going to be 7 joules. All right, so for part B, it wants to know the x-coordinate of any points at which the object has 0 kinetic energy. Well, the total energy that we just calculated is constant, 7 joules. So for the object to have 0 kinetic energy, that must mean that it has 7 joules of potential energy. So we just set the equation for potential energy equal to 7, and we can solve that. There are two solutions. It's going to be plus or minus root 7 divided by 2. So on the graph, these would correspond to the 2 points where our parabola intersects a horizontal line. This horizontal line here represents the total energy, which is 7 joules. So that will intersect the graph at these 2 points. They'll be symmetric about the origin, and we call these, remember, turning points, because that's where the object has 0 kinetic energy. When the object reaches those points, it will stop, turn around, and start going in the other direction. All right, so part C. Part C asks us to find the magnitude of the momentum of the object at x equals 0.6 meters. Okay, so we have to take a few steps to get here. The first thing we can calculate directly is the potential energy at that location. So when x equals 0.6, the potential energy is 4 times 0.6 squared, which is about 1.44 joules. Since we know the total energy is 7 joules, the kinetic energy must be 7 minus 1.44, which is 5.56 joules. Okay, so we can set this equal to the formula for kinetic energy, 1/2 mass times velocity squared, and then we can solve for the velocity and then find the momentum. Or if we want to take a slight shortcut, remember kinetic energy is also momentum squared over 2 times the mass. So the momentum squared will be 5.56 times 2 times the mass. So either way you solve it, the momentum should come out to be about 5.78, and the units, kilogram meters per second. Make sure you always include the units on all of these answers, by the way. One of the points on this problem actually comes from just having correct units on all parts of the problem. All right, and then lastly, part D, calculate the magnitude of the acceleration of the object as it passes x equals 0.6. So for this, you have to remember one of the main ideas from this topic. We called it the big picture in one of our assignments. And that is that you can determine the force on an object from a graph of its potential energy versus position. And that relation is that the force is equal to the negative derivative of potential energy with respect to position. So this requires a little bit of calculus. We're taking the negative derivative of the function 4x squared, so that gives us minus 8x. So that means when x equals 0.6, the force acting on this object is minus 4.8 newtons. So the acceleration will be force divided by mass. The mass is 3 kilograms, so that is minus 1.6 meters per second squared. The problem asks for the magnitude of the acceleration, so that's just the absolute value. That will be 1.6 meters per second squared. All right, so that takes care of problem 1. If you're curious about the point allocation, we have, there's actually one more part on the next page, so hold that thought. All right, so last part of this problem asks you to fill in a couple of graphs. So on these axes, we want to sketch the position versus time and kinetic energy versus time. So it says assume that x equals 0 at time t equals 0. So we can really start with that point. And we want to show how this object moves. So I mentioned at the beginning that since this has a parabolic or quadratic potential energy function, we know that this is going to yield simple harmonic motion. And with simple harmonic motion, the graph of position versus time looks like a sine wave. So the position will go back and forth between some maximum and minimum values. They will be equally spaced with regard to the time axis. We actually calculated these values. This is plus and minus root 7 over 2. And we're just going to get some kind of sine wave that goes back and forth between these points here. So what about the kinetic energy? Well, the kinetic energy will oscillate as well. So we can try to line up my horizontal axes here. Kinetic energy, of course, cannot be negative, so that's going to go back and forth between 0 and some positive value. So when is kinetic energy 0 and when is it maximum? Well, the kinetic energy is 0 whenever the velocity is 0. So the velocity of the object is 0 whenever the slope of the position versus time graph is 0. So these points marked by blue dots, which happens twice per cycle, those are the points where kinetic energy is 0. And then kinetic energy will be maximum whenever the position is 0. So at all of these points here, the kinetic energy is going to have its maximum value. And then we always have some sine function that connects those. So notice what happens here. We get a sine wave for both of these graphs, but there are two key differences. The kinetic energy graph is strictly positive. It goes back and forth between 0 and a maximum value instead of a negative value and a positive value. But also the frequency of the kinetic energy graph is double that of the position graph. There are twice as many cycles in the kinetic energy graph as in the position graph. So make sure you don't get careless about that if you see a problem like this on the AP test. Okay, so as for point values here, A is worth 2 points, and then B, C, D, and E are each worth 3 points. This adds up to 14, so if you're wondering where that last point is, as I mentioned before, the last point is for having correct units on all parts of this problem. All right, so moving on, let's look at question 2. Question 2 involves this rectangular bar which is suspended from a pivot. So I think we had one sort of similar to this on a previous test. All right, so it says this thing has a total length L, and then X marks the distance from the pivot to the center of mass of this object. So the center of mass is not necessarily in the center of the bar. It's not a uniform bar. In fact, you're specifically told it has a non-uniform mass density. So we want to figure out the rotational inertia of this bar by allowing it to swing essentially as a physical pendulum. Right. So in question A, let me move this around a little bit. Here we go. In question A, we're asked to find the equation of motion for this bar. So the equation of motion for this bar will be some sort of differential equation. So to remember how to set that up, first let's look at what would happen if we displaced this bar by some angle. So I'll mark the center of mass here. All right, so let's say we've displaced it by some angle theta marked here. There's going to be a restoring torque acting on this bar to try to swing it back towards equilibrium position. So that restoring torque is going to come from the gravitational force acting on the bar. So we have this force mg acting at the center of mass. So we still have this distance x here. So this force mg creates a torque around the pivot, and that torque is equal to force times the distance from the pivot to the location of the force, which is x, multiplied by the sine of theta. So remember, a torque is really a cross product of two vectors, but in 2 dimensions, what that boils down to is just having this sine theta factor here. And we're actually going to say that this torque is negative because it's a restoring torque. It tends to decrease theta. So the equation of motion here is Newton's second law. Torque equals moment of inertia times alpha. So the way we write this as a differential equation is to remember that alpha is really the second derivative of theta with respect to time. So remember, omega, that's the angular velocity. That would be the derivative of theta with respect to time. Alpha is the derivative of velocity with respect to time, which ends up being a second derivative of the angular position. So if I combine all of these equations, I have torque, which is minus mgx sine theta, equals I times the second derivative of theta with respect to time. So this is our answer. This is called a differential equation because we have a derivative of some function and the function itself both present in this equation. So that generally makes it harder to solve. This is an entire class of equations, but in physics, this particular type of differential equation does turn up a lot for oscillations. All right, this is actually just part I of part A. So for the second part, it tells us to apply the small angle approximation to calculate the period. So this equation that we arrived at in part 1 is actually not solvable by any techniques that we know. But we can use this thing called the small angle approximation which says that if an angle is sufficiently small, say about 10 degrees or less, then the sine of theta is approximately equal to theta itself, as long as we are working in radians. So if we rewrite the equation in that form, we can just replace sine theta by theta itself. Sorry, I'm missing the squared on the t down here. Okay, so we can rearrange this a little bit. Let's put both terms on the same side of the equation, and let's divide both sides by the moment of inertia. So we get something that looks like this. All right, so this is the simplified form of the differential equation, and this is actually something that we can solve. So what we want to remember is that theta is itself a function of time. So this is a function that says if we take the second derivative of this function, it is proportional to the function itself. Maybe it's more clear if we write it this way. So if I take the second derivative of the function, I just get the function itself multiplied by some negative constant. So that suggests we have some sine or cosine function. So as a reminder, if I say that this function theta is equal to a times cosine of omega t, then if I take the derivative of this function with respect to time, that is minus a times omega sine omega t, and if I take the derivative again, the sine turns back into a cosine, I get another factor of omega out in front. So this is just minus omega squared times, our initial function. So if you compare these two expressions here, one just differs from the other by this factor of minus omega squared. So we are going to set that equal to this form up here. So the second derivative of theta is equal to minus omega squared, which is this, times our original function. So that tells us that our omega, the angular frequency of this oscillation, is just the square root of whatever we had out in front. And since we're asked for the period, this is equal to 2 pi over the period. So we can rearrange this and say that the period is equal to 2 pi times the square root of the moment of inertia over mgx. All right. So that is the period of motion. So m is known, x we're told in the problem is known. So if we just measure the period of this physical pendulum, then we can plug everything into this equation and determine what the moment of inertia is. All right, so that's actually what we need to explain in part B. Part B asks us to describe an experimental procedure that we could use to determine this moment of inertia. So really all we have to do is say, displace this by a small amount, a small angle, allow it to swing, measure the period, and then plug everything into this equation and find the moment of inertia. There's really not a whole lot to part B to justify how many points it's worth. It's worth 5 points in this problem. But one thing that you should mention, it asks for how to minimize experimental error. So the way we minimize experimental error is to count the time for 10 oscillations, and then divide that by 10 to get our measurement of the period instead of just counting one oscillation. All right, so to keep track of where we are here, for part A was actually worth 8 points. Each subpart was worth 4 points apiece. Part part B is worth 5 points. So that's most of the value of this problem here. The final 2 points are from part C. So part C says, now suppose you don't know the location of the center of mass. So this length x that's marked in the first figure is unknown. Describe a procedure that you could use to determine where the center of mass of this object is. So we're talking about this value here, which is, now we're going to say unknown. So one thing we know about the center of mass of an object is that an object should balance on its center of mass. So really all you need to do is just grab a fulcrum, place this bar on top of the fulcrum, and then shift it around until you find the point where it balances. That will give you the location of the center of mass. And then that's really all you have to do. You can simply measure the distance from the one end of the rod to this balancing point, and then you're back to where you were. You know everything else, so you can now find the moment of inertia using the same procedure as in part B. So this is really all you have to remember for that part. If you can balance something on a fulcrum, then that tells you the center of mass is directly above the fulcrum. Okay, so we've got one more problem here. All right, so this problem starts off with an Atwood machine, or a modified Atwood machine. So we have two blocks of mass m/2 connected by a rope. One of them's on a frictionless table, so there is no friction here. And then the other one is suspended over the end of the table. All right, so the first question is to find an expression for the speed of the hanging block as a function of the distance that it descends. So this can be treated as a conservation of energy problem. The change in kinetic energy is going to equal minus the change in potential energy. So the potential energy, delta U, will be negative as the block falls, so minus delta U will be positive. And the negative change in potential energy will be the mass m/2 times g times the distance. The kinetic energy is 1/2 mv squared. Whereas here you have to remember that both blocks are moving with the same speed. So the kinetic energy will be 1/2 times the total mass, m, not m/2, times v squared. And we're calling this vh. So if we solve this, the 1/2 m's will cancel on both sides. So vh is just the square root of g times d. All right, that was worth 4 points on this problem. Part B says determine an expression for the force of gravity on the hanging part of the rope. Okay, so I have to show the next picture here. So now we're going to say that we will replace these two blocks with a rope. So this rope has a length L, so the length of the rope is the same as the length of the string in the first picture. And the total mass of this rope is the same as the total mass of the two blocks in the first part. So some things are the same, except that we're just changing how the mass is distributed over the length of the rope, if you want to think of it that way. Okay, so we're told here that the rope just hangs slightly over the edge, the table is still frictionless, and then we're going to release the rope from rest, and it's going to start sliding off the table. All right, so for part B, we just want to find an expression for the force of gravity on the hanging part of the rope. Well, the force of gravity on any object is just equal to its mass times gravity. So the question becomes, what is the mass of the hanging section of the rope? Well, if the length of the hanging section is y and the total length is L, then the fraction y over L should give us the fraction of the total mass which is hanging off the edge. So the mass of the hanging section of the rope will just be y over L times m. So that times g is equal to the force of gravity. So that is our answer to part B. That's worth 2 points. Okay, so the next part, C, is worth 3 points. It asks us to find an expression for the work done by gravity on the rope as a function of y, assuming y is initially 0. So there are 2 ways we could do this, maybe one easier, one less so. So one way we could do this is to use the definition of work. So work is an integral of force over displacement. Now, we cannot just take the answer that we got to part B and multiply it by a distance, because the answer to part B is not a constant force. It depends on y, so as the rope falls, that gravitational force increases linearly with the length of the rope that's hanging over the edge. So since this is not a constant force, we have to use an integral to find the total work done as a certain length of rope falls. So we could integrate the force, which is y over L times mg times dy, and then we'll integrate this from 0 to y. If you don't like using the same variable for the limits as in the integral itself, we can call this something different, like y prime. So if we integrate this, we get mg over L, those are all the constants. Y prime becomes 1/2 y prime squared. And we evaluate that from 0 to y. So we get mg y squared divided by 2L. All right, so that's our answer. That's one way we could have gotten it. If you're less comfortable with doing integrals, the other way we could solve this is to say that the work is equal to the negative change in potential energy. So we have to think a little bit more carefully about this. So let's go back to this picture here. So what is the change in potential energy between the rope when it is entirely on the table surface and when it is as pictured here with part of it hanging off the edge? So part of the rope has been lowered by some amount. So this part that I've circled has dropped by a certain distance. So how do we really calculate that? Well, if we look at the center of mass of this part of the rope, we can say that the change in potential energy will be the mass of this part of the rope multiplied by g multiplied by the distance that the center of mass has descended. So this will be minus the mass of that section of rope, which is y over L times m, times g, times the displacement of the center of mass, which is minus 1/2 y. So if we do that, the minus signs cancel, and we get, once again, mg y squared over 2L. All right, so we're almost there. Part D is next. That's also 3 points. D asks us to find an expression for the speed of this rope as a function of y. Well, we know the change in potential energy now. It decreases by this amount, mg y squared over 2L. So we can just set that equal to the kinetic energy. So the kinetic energy of this rope will just be 1/2 m times v squared, and we're calling this v rope this time. All right, so again, remember the entire rope is in motion with the same speed, so we have to use the full mass m on the right-hand side. So we can cancel the 1/2 m's again. So we'll get Vr is equal to the square root of gy squared over L. Or if you want to pull the y outside the square root, this will be the expression we get. All right, so last part, also 3 points. Part E says that the hanging block and the right end of the rope are each allowed to follow distance L the string is long enough so that the sliding block doesn't hit the pulley, and it wants to know whether the hanging block is moving faster or the rope is moving faster once they both traveled the same distance. All right, so here we just need to compare the answers that we got for parts A and D. So the hanging rope velocity was given by the square root of g times d. So if we let it fall a distance L, that becomes g times L. The velocity of the rope, again, we're going to plug in y equals L. So if we do that here, we'll get the square root of GL squared over L, or square root of GL. So it turns out that these are actually the same. So our answer here is that the speeds are equal. And your justification is just pointing to the expressions that you got for parts A and D. All right, so that should cover all of the parts of these questions. Again, if you have any questions after seeing this, please let me know and I will try to straighten things out. All right, thanks and have a good day.